Since stationary, in the previous day we discussed about stationary random process. Now we will discuss about wide sense stationary process. It is really difficult to have a strict sense stationary process. Therefore, we allow the wide sense stationary processes. What is the condition for that? One is mean should be independent of time shift of origin. That means you are taking the mean at time t1 and you are taking the mean at time t2, or you are shifting the origin and taking the mean. This should be independent of time shift. Okay, and another is autocorrelation of any two instances. Okay, that should be independent of time t1 and t2, that is rx t2 minus t1. So the basic difference between this stationary and wide stationary is that we are considering up to the first moment and the autocorrelation. If these two conditions are satisfied, then we can call it as wide sense stationary, where for strict sense stationary the joint probability density function of any order should be same or should not depend on the shift of time origin. But here we are considering only up to two random variables or two time instances, and their autocorrelation should not depend on time 1 and time 2, rather will depend on difference between t2 and t1. In case of ergodic process, what happens? That you are taking the ensemble average. And what is time average? Time average means you are considering a single waveform and you are calculating the average over a time. Okay, if this time average of a waveform, of each waveform, is equals to ensemble autocorrelation of the whole random process or ensemble, this one, and another is ensemble autocorrelation is also the time autocorrelation of any sample space, then we will call it as ergodic process. Time autocorrelation, see these two terms, one is time average, another is ensemble average. Time average means you are considering a single waveform, taking the average over time, that is time average of any sample. And ensemble average means you are considering the whole process and taking the average. Similarly, for time autocorrelation means autocorrelation of a sample between 2 points, and if it is same to that of ensemble autocorrelation, that means of the whole process or random process, then we will call it as ergodic process. Okay, now we will discuss another important topic, that is how to calculate for a wide sense stationary power spectral density. For a wide sense random process, you can consider that it is a periodic, it is varying from minus infinity to plus infinity. Therefore, representing in the frequency domain by Fourier transform is difficult, because the condition of Fourier transform that the signal should be absolutely integrable, but as it is varying from minus infinity to plus infinity, we cannot get a finite integration. That this is why we consider what? We consider a truncated version of the signal and calculate the autocorrelation function and vary this capital T from minus infinity to plus infinity. Later stage, the total calculation has been shown in my note, and we have seen that the result is Fourier transform of this autocorrelation function will give us power spectral density, and from the power spectral density we can have this power by integrating the power spectral density. And in another way, we can also get the power from the autocorrelation, because autocorrelation at tau equals to 0 is nothing but mean square value of the process. That will also give me the power. Now, we'll compute another important thing, that is band pass random process. You have a band pass random process and you want to calculate the power spectral density of that. Okay, and if you can remember, and I have given in this note also, that a band pass random process can be represented in terms of low pass random processes XCT and XCS. Okay, now if we see that XT is represented at XC cos omega CT plus theta and XS sin omega CT plus omega, where XC and XS is spectrum or power spectral density is low pass, and if we see here that XCT is obtained by multiplying XT into 2 cos omega CT. Okay, therefore if we consider a power spectral density of XT, and if we multiply it by 2 cos omega CT, therefore the power spectral density will become Sx omega plus omega C plus Sx omega minus omega C. Now as we are passing it to a low pass filter, therefore now what you see what happens peculiarly, this is very important part, that if it is XT and if it is the power spectral density of XT, and if you multiply this by 2 cos omega CT, then what is happening? X of omega plus omega C and X of omega minus omega C. Consider this part, omega minus omega C and omega plus omega C. That means you will get one at 2 omega C and another will be down converted to centered at 0. Similarly for this part also we will get one at minus 2 omega naught and another at 0. As both the spectrum are up converted and down converted, we have got 4 such waveforms. And from this figure you can see that ultimately to get XCT we are passing it through the low pass filter, therefore these two parts will be eliminated and finally we will get this one. Okay, this is very important part. We will see whatever we have done, calculation we have done for to check the performance of modulated signal in the presence of noise, and we will see how band pass random processes or power spectral density are calculated to have the power. And we can also see from here that the power of this associated with this power spectral density, and for XC part power spectral density and power spectral density for XS part all are same, because it is quite natural. You see this is a part and this is a part. For XT power spectral density you are taking the integration, for XCT part or XS part you are getting this one, twice of this or addition of these two. Same, both are within the range of 4 pi b, therefore power of the XCT signal and XS signal and XT signal all will be same. In this connection, I will tell another important thing, that is the white Gaussian noise.